Hello, this is Senior Design Group 12 demonstrating our progress with the polyphonic analog to MIDI converter. In this video, we will show the current state of the preamp section, the note detection algorithm, the MIDI output circuit, and the operation of the analog to digital converter. The requirement specifications that we are focusing on are the gain and operation of the preamp section, the accuracy of the note detection algorithm, the ability of the MIDI circuit to sense the output data of the MSP430, and the sample rate and latency of the ADC.
This is our breadboard for the preamp section. The main goal for the breadboard is to normalize the voltages of the input to between about 0 and 2 volts, as well as cut out any extraneous frequencies that may cause aliasing. So there's a active bandpass filter that does that. And some of the features include a buffered bypass, so that way you can split your signal off and use your unaffected signal with other devices without having to add your own signal splitter before going into this device, as well as a switch, which in this case there's two separate switches, but it'll be one 3-pole double throw switch that does everything at once, that changes between line level and mic level, so it adjusts the amplifier gain to adjust for that. And then also there is a potentiometer, so you can adjust the gain along with this LED that serves as a clipping indicator. That way you can adjust the gain right up to the edges of its range and then lower it just a little bit so it doesn't clip, but it maximizes the signal to noise ratio, and helps normalize your magnitude so that your loudest note is about the loudest note you'll have coming out of the MIDI conversion. And then you can see the oscilloscope here. Right now we have a waveform generator set to 300 millivolts peak, so 600 peak to peak, which is right within line level range. And you can see that right now it's about dialed in, but if you increase it just a little bit, it'll start to shine the LED to let you know that it's going past the range that it should be. And then if you take it just below that, it'll pull it back within the range, and you can see if I do it again, you can see it go past the range it's supposed to be in. And then you pull it back, it goes back within the range again. And then it can show it with line level as well, or mic level rather, which is, this line level is usually about 300 millivolts or to 2 volts, while mic level is usually about 5 millivolts to 50 volts. So if we put, let's say, like 15 millivolts peak, so 30 peak to peak, which is right within mic level range, you can see it's really low here because we haven't switched it to line level yet. And then we switch it here to the mic level rather, and then you can see here we can attempt to dial it in. The issue right now is that the function generator on this device right here actually has a really high noise ratio. So when you use really small voltages, like in the like 2-digit millivolt range or so, it gets a lot of noise, as you can see. But you can see in general, if I like consistently shine it, get it to consistently shine bright and then go a little below that, you can see it's about where it's supposed to be. If you were to look at like the averages of where the peaks are, and if the voltage range was clean, or the voltage generator was clean, then it would be a little nicer looking, but it does what it's supposed to do. I'll be demonstrating our note detection algorithm. I'll be showing the testing process as well as the output for a couple tests for a previous version of the algorithm, because right now our current version we're making changes for optimization purposes, as well as some tweaks we've made to the FFT since then. So that version's not completely functional as of right now, but we do have some good output from a previous version. So to test it, I first would run an audio file of a guitar playing chords through FFT in MATLAB, and you can see here's a graph of that. And in this case, we have the magnitude normalized to 128 to represent the 7 bits input we'll be getting from the ADC. But in the previous case, we didn't. In the previous version that I'll be showing the output from, the magnitudes aren't normalized, so we get some weird magnitudes there. But then we also have our output here, then which I copied and pasted into the note detection algorithm into the array that would be filled by the FFT on the MCU instead when this is uploaded to the MCU. And then I'll show a couple tests that we have. So here's the first test that we did. You could see the output in here is in the form of just showing the bins as well as the approximate frequency of that bin, and then magnitude, which in this case are garbage values. And the first test is using this audio file. So you can hear it plays, the guitar is playing 5 different notes consecutively, so they're all ringing out at the same time, forming a chord. And those 5 notes do correspond here. And then there's also an extra octave note of the, this is the E5, I believe. That's an octave of the highest note due to some of the harmonics. Since there's multiple E's being played, it doubles down on the harmonics, so it thinks there's a note here in this case for this old version, and so that gives us an accuracy of 5 out of 6, which is pretty high and well within our margin that we have right now. And then you can see this one right here. That one is of an acoustic guitar playing a chord, and that's we figured we use an acoustic recording as well, since that'll be closer to what the input we'll be getting from a microphone would be. And you can see the output of that here. And in this case, all 4 notes are accurate, which is really good. And let me just show that these notes are equivalent. So in this case, we have E3, G3, C4. Let's just do like E3. So we have 166, 198. Sorry. 166 approximates to this, and then 193 approximates to this. So E3, G3, and you can see that those are the right notes for that.
This is a test of the MIDI output circuitry this is a prototype for the MIDI output circuitry. So here is the MSP 430 FR5994 development board, and some of those pins are connected here. So what this does is it outputs a basic UART signal at 31.25 kilobauds, and then it loops back into the microcontroller through a digital input pin, and it outputs through a digital output pin the inverse of what it receives through that pin. And what the output pin does is it drives this transistor here, which allows it so that either around 5 milliamps or 0 milliamps is passed through the connection, and that allows the microcontroller to send MIDI data to this MIDI to USB converter cable. And right now I have that connected to my computer here, and what it's set to do right now is it's set to output middle C repeatedly. And so if I click record, you'll see that the program receives a bunch of middle C's, and it will keep going and going. So this is a test of the ADC sample rate. Here's the microcontroller. The ADC is configured to take samples at 12.5 kilohertz. and right now the ADC is set up to toggle a digital output pin every time it takes a sample, and here it is hooked up through an aux cord to my computer so we can see the signal. So if I click record and I do one iteration, alright, so the part that we're interested in is over here. So here we can see the waveform of the output signal. So if we grab one of these pulses, we see that the length is actually 6 samples, and I'm recording this at 96 kilohertz, so that corresponds to let's see, that corresponds to a frequency of around 16 kilohertz for this waveform, which is to be expected because this is very inaccurate. So if we take this one for example, here it says the length is 8 samples, and so 96 kilohertz divided by 8 is 12 kilohertz. So this this kind of confirms that our sample rate is around 12 kilohertz, although much better, more precise tools are needed to completely verify that that's the case. But so far we're on the right track when it comes to the sample rate. This is a test of the stream latency of the system. Right now it is set to, right now I'm measuring how long it takes between gathering a set of samples and outputting the FFT. So here here the system is set to toggle this LED and the signal that's connected to my computer. It's set to toggle that every time it finishes one iteration of the analog signal input gathering. So as you can see, it's repeatedly doing this. So if I click record, we get some data. So each pulse here corresponds to one iteration. So if you measure the length of the pulse, it is around 5,634 samples at a sample rate of 96 kilohertz. So if we divide 5,634 divided by 96,000, we get roughly 58.7 milliseconds, and that is within our latency requirement of 100 milliseconds. Now, this does not include the note detection algorithm, but since the runtime of the algorithm is linear, and we are working with in total around 384 points in total, the latency will be very minimal. The difference in latency will be very minimal. and that's it.